Hello everyone, my name is Alric. So we have studied a lot of cycles in applied thermodynamics. Otto cycle, diesel cycle, Ericsson cycle, Stirling cycle. Out of all these, Otto and diesel are the most famous cycles which all of you must be knowing, right? So we have to compare out of these two cycles under different conditions which are the best cycles. Now for example, I'll say recently now IPL is going on. So there are suppose two cricket players, say X and Y. We must compare them. So how do we compare them is we have to have a common measure between them and we must see under what conditions they perform well, under what conditions they are more efficient. Okay, so if there are parameters like wicket keeping and scoring more runs. So player X might be very good at wicket keeping and player Y may be very good at scoring more runs. Okay, so this is how we take a common measure between them. On a similar fashion, when we have to compare between Otto and diesel cycles, we need certain parameters to compare them. Okay, in that parameters, one of the most few variables which I would say is the compression ratio. Okay, the compression ratio, peak pressure, that is the maximum pressure, and heat addition, heat rejection, and the net work output, so that you can see in the slide. So in order to compare the performance of these cycles, some of the variable factors must be fixed. Comparison is made to analyze which cycle is most efficient for a given set of operating conditions. So I have another example for you guys. Suppose there is a race, running race, and 10 of them are running, and we must know that who runs faster or slow than the other person. Suppose we say the guy A who is leading is 5 times faster than B, or we can say the third guy, the C guy, is 10 times slower than the B guy. Okay, so how do you measure these? So we keep one of the guy constant. Suppose if I say A is running faster than B, that means B is kept constant and A is measured with reference to B. When I say than B, A is measured with reference to B. So on a similar fashion, if we have to compare these variables in the Otto and diesel cycle, we have to fix a few variables in that. For me, I have to be doing that is equal compression ratio and heat addition. So what we are fixing here is we are fixing the compression ratio and the heat addition. Okay, before worrying about the comparison between Otto, diesel and all that, let me first show you how an Otto cycle looks. This is the first, when you see the first diagram in the picture is the TS diagram of Otto cycle, which is what we want. PV diagram is for work, TS diagram is for heat, right? So TDS is equal to Q. So in the second picture I've shown the TS diagram for Otto cycle, in which amount of heat supplied is given. So area under the curve 2, 3 is the amount of heat supplied. Similarly, in the third diagram, the area under 1 and 4 is the amount of heat rejected. So we must know the work output. Okay, so from the first law of thermodynamics, we have Q is equal to delta U plus V. So change in internal energy, that is delta U, is equal to 0. Why? Because this is a closed cycle and in internal there is no change in internal energy. So net heat transfer is equal to work output, which is net heat transfer is equal to heat supplied minus heat rejected. So this is for the Otto cycle, the TS diagrams for Otto cycle, amount of heat supplied and amount of heat rejected. So on a similar fashion, we have the TS diagram for diesel cycle, in which I have mentioned the TS diagram for diesel cycle, amount of heat supplied and amount of heat rejected, the same way. Only thing is, in diesel cycle, the heat addition is in constant pressure process. Heat addition is a constant pressure process. So next we come to the comparison factor, which is very important for us now. So in the TS diagram of Otto and diesel cycle, 1, 2, 3 and 4 is the Otto cycle, 1, 2, 3 dash and 4 dash is the diesel cycle. So you can see the shaded portion, which is A, B, C, D, E, F. It is evidently visible that the area under diesel cycle is more, so the amount of heat rejection in diesel cycle is more. So now let's talk about the efficiency. Efficiency is given by work output divided by heat input. So from first law we saw work output is Q supplied minus Q rejected divided by Q supplied, that is heat input, right? So efficiency is equal to 1 minus Q rejected minus Q supplied. So let's assume some values and let us check out which is more efficient. So in the first case, I've taken heat rejected as 4 and heat supplied as 8, and Q rejected is 6 and Q supplied is 8 in the second case. Q supplied is the same in both the cases because heat addition is same in this condition, and the compression ratio as well. So efficiency, you can see that 1 minus 4 by 8 is 50%, that's 0.5, and in the second case efficiency is 1 minus 6 by 8, which is 0.25. so clearly we can see that increase in area of heat rejection decreases the efficiency. So in this case, diesel cycle has more area of heat rejection, so diesel cycle is less efficient than Otto cycle under this condition, which is equal compression ratio and heat addition. So there's another cycle which is dual cycle, which is a combination of both the cycles, so that comes in between. So under this condition of equal compression ratio and same heat addition, Otto cycle is more efficient than dual cycle, and that is more efficient than diesel cycle. Thank you.